An Ufer ground is a metal grounding electrode connected to underground metal water pipes and serves as part of the primary grounding system for a building. A ground rod, on the other hand, is a metal rod driven into the earth and connected to the electrical system to provide a secondary grounding path. Typically, an Ufer ground is sufficient for grounding a building. However, a ground rod might be necessary as a supplementary grounding path if there is no underground metal water pipe system, or if the Ufer ground is not adequate for the electrical load or fault current. The requirement to separate grounds and neutrals at the main panel is correct and is mandated by the National Electrical Code, or NEC. Ground provides a path for fault currents to flow to earth, while the neutral provides a reference point for the electrical system and carries return current. Connecting grounds and neutrals together can create a potential safety hazard, potentially causing fault current to flow through the neutral wire instead of the ground wire, which can lead to electrical shocks or fires. It is important to discuss the specific reasons for requiring a ground rod, even with an existing Ufer ground, with the inspector to fully understand the situation. Ground rod installation should be performed by a qualified electrician. If you are not comfortable separating the grounds and neutrals, it is advisable to hire a licensed electrician. Let's delve deeper into the technical aspects of grounding and the reasons behind these requirements. The purpose of a grounding system is to provide a low impedance path for fault current to return to the source. This path allows overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and de-energize the circuit in the event of a fault, preventing electrical shock and fire hazards. The Ufer ground, named after Herbert Ufer, utilizes the concrete encased electrode, typically the reinforcing steel in a building's foundation, as a grounding electrode. Concrete is a relatively good conductor of electricity, especially when it is in contact with the earth. This type of ground is considered a very effective grounding method because of the large surface area in contact with the earth. However, the effectiveness of a Ufer ground can be affected by factors such as the moisture content of the soil, the type of concrete used, and the size and configuration of the reinforcing steel. A ground rod, on the other hand, is a simpler grounding method that involves driving a metal rod, typically made of copper or copper-clad steel, into the earth. The effectiveness of a ground rod depends on the soil resistivity. Lower soil resistivity results in better grounding. Factors such as soil type, moisture content, and temperature affect soil resistivity. In areas with high soil resistivity, multiple ground rods may be required, connected in parallel to achieve the required grounding resistance. The NEC provides guidelines for grounding and bonding to ensure electrical safety. Section 250.52 details acceptable grounding electrodes, which include metal underground water pipes, the metal frame of the building or structure, concrete encased electrodes such as Ufer grounds, and ground rods. Section 250.53 specifies the requirements for ground rods, including the minimum size and depth of the rod, and the spacing between multiple ground rods. The requirement to separate grounds and neutrals at the main panel is based on the principle that the neutral conductor should only carry current during normal operation, while the ground conductor should only carry current during fault conditions. When the neutral and ground are connected together at multiple points, it creates parallel paths for current to flow. This can result in a portion of the neutral current flowing through the ground conductor, which can create a voltage drop on the ground conductor and potentially energize metallic parts of equipment, creating a shock hazard. In a properly wired system, the neutral and ground are bonded together only at one point, typically at the service entrance. This ensures that the ground conductor remains at or near earth potential during normal operation and provides a low impedance path for fault current to return to the source. The NEC requires that the grounding electrode conductor, which connects the grounding electrode to the neutral bus at the service entrance, be sized according to Table 250.66, based on the size of the service entrance conductors. The grounding electrode conductor must be large enough to safely carry the maximum fault current that could occur on the system. The separation of grounds and neutrals is typically achieved by using separate busbars for the neutral and ground conductors in the main panel. The neutral busbar is connected to the neutral service conductor, while the ground busbar is connected to the grounding electrode conductor and the equipment grounding conductors. Equipment grounding conductors are the wires that connect the metallic parts of equipment, such as enclosures and conduit, to the ground bus bar. These conductors provide a low impedance path for fault current to return to the source in the event of a fault within the equipment. The size of the equipment grounding conductors is determined by Table 250.122, based on the size of the overcurrent protection device protecting the circuit. It is crucial to ensure that all electrical connections are properly made and tightened to minimize resistance and ensure a reliable grounding system. Loose connections can create hotspots and increase the impedance of the grounding path, which can reduce the effectiveness of the grounding system and increase the risk of electrical shock and fire. Regular inspection and testing of the grounding system is recommended to ensure that it is functioning properly. Ground resistance testing can be performed to measure the resistance of the grounding electrode to earth. A low resistance value indicates a good connection to earth, while a high resistance value indicates a potential problem with the grounding system. In some cases, the inspector might require a ground rod in addition to a Ufer ground due to specific local conditions or requirements. For example, if the soil resistivity in the area is high, a ground rod may be needed to supplement the Ufer ground and ensure that the grounding system meets the required resistance to earth. Another reason for requiring a ground rod is to provide redundancy in the grounding system. If the Ufer ground were to become damaged or compromised, the ground rod would still provide a grounding path, ensuring continued electrical safety. In addition to the NEC requirements, local codes and regulations may also have specific requirements for grounding systems. It is important to consult with the local electrical inspector or a qualified electrician to ensure that the grounding system meets all applicable requirements. When installing a ground rod, it should be driven into the earth to a depth of at least 8 feet according to the NEC. The top of the ground rod should be flush with or below ground level to prevent it from being a tripping hazard. If multiple ground rods are used, they should be spaced at least 6 feet apart. The grounding electrode conductor should be connected to the ground rod using a listed connector. The connector should be suitable for direct burial and should be installed according to the manufacturer's instruction. When separating grounds and neutrals in the main panel, it is important to carefully identify all of the neutral and ground conductors and ensure that they are connected to the correct bus bars. Incorrectly connecting a neutral conductor to the ground bus bar or vice versa can create a dangerous situation. It is also important to properly torque all of the connections to ensure that they are tight and secure. A torque wrench should be used to tighten the connections to the manufacturer's specified torque value. After completing the grounding system installation, it is important to test the system to verify that it is functioning properly. A ground resistance tester can be used to measure the resistance of the grounding electrode to earth. An impedance tester can be used to measure the impedance of the grounding path. These tests can help identify any potential problems with the grounding system and ensure that it is providing adequate protection against electrical shock and fire hazards. In summary, a properly designed and installed grounding system is essential for electrical safety. The Ufer ground and ground rod are both acceptable grounding electrodes, but the choice of which to use depends on the specific conditions of the installation. The separation of grounds and neutrals at the main panel is a critical safety requirement that must be followed to prevent electrical shock and fire hazards. Regular inspection and testing of the grounding system is recommended to ensure that it is functioning properly. Always consult with a qualified electrician or electrical inspector to ensure that the grounding system meets all applicable requirements. Let's further elaborate on the importance of grounding in different scenarios and some additional considerations. In residential settings, grounding protects individuals from electrical shock by providing a path for fault current to flow back to the source, tripping the circuit breaker and energizing the circuit. This is particularly important in areas where water is present, such as bathrooms and kitchens, where the risk of electrical shock is high. In commercial and industrial settings, grounding protects both people and equipment from electrical hazards. Grounding can prevent damage to sensitive electronic equipment from voltage surges and transients, and it can also reduce the risk of fire caused by electrical faults. In addition to the NEC requirements, there are also industry standards and best practices for grounding. The Institute of Electrical and Electronics Engineers, or IEE, publishes standards for grounding and bonding of electrical systems, which provide more detailed guidance on grounding design and installation. When designing a grounding system, it is important to consider the potential for lightning strikes. Lightning can cause significant damage to electrical equipment and can also create a serious safety hazard. A properly designed grounding system can help to protect against lightning strikes by providing a path for the lightning current to flow to Earth. Lightning protection systems typically include lightning rods, which are installed on the roof of the building, and grounding conductors, which connect the lightning rods to the grounding electrode system. The grounding electrode system should be designed to have a low impedance to Earth to effectively dissipate the lightning current. In some cases, it may be necessary to use a separate grounding electrode system for the lightning protection system to prevent lightning current from flowing through the building's electrical system. When working with electrical systems, it is always important to follow safe work practices. Always to energize circuits before working on them, and use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you are not comfortable working with electrical systems, it is best to hire a qualified electrician to do the work. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical inspector before making any changes to your electrical system. Understanding the nuances of grounding systems is crucial for ensuring electrical safety and preventing potential hazards. Grounding is not just about meeting code requirements, it's about creating a safe environment for people and protecting valuable equipment. By adhering to best practices and seeking professional guidance, you can ensure that your grounding system is effectively safeguarding your property and those within it. Remember that electrical codes and regulations can vary depending on your location, so it's essential to stay informed about the specific requirements in your area. Furthermore, advancements in technology are constantly leading to new and improved grounding methods and equipment. Staying up to date on these developments can help you optimize your grounding system for maximum effectiveness. Grounding is an ongoing process that requires regular inspection, testing, and maintenance. By taking a proactive approach to grounding, you can minimize the risk of electrical hazards and ensure the long-term safety and reliability of your electrical system.